in interdependencies and with respect to the master guidance. So what about the position with respect to this? This 20 is how it is managed. This 20, how it is managed? Is there a unique rule? What about the deviation? What about the orientation? How do you control? Nobody knows, because the classical approach deviates along a diagonal more, because if you go for a 0.2 tolerance from the center, it is 0.4. And what about the diagonal? We are not getting 0.4 by 2. This is not 0.2. That is the problem. The classical tool controls the location of the bore axis with a square tolerance zone. Why should we? So why should we go for this classical tolerance zone? Okay. So I think you are getting disturbance for this poll. So now you can able to see my screen. Yeah, so I'm very sorry, because what I was trying to discuss. So since when you are not able to hear the screen, so what I will do is just I will brief it once again. So I think this is a very important part which I skipped. So let us say we are going to understand this classical approach with this particular pin and the shaft. The 6 different bores are available here, and these different locating pins are available here. The mutually oriented locations for these pins between is 0.2 mm, and from the edges it is 2 mm. So this is the CAD model, and this is the tolerance. In the conventional way, without GD&T, how do you do? So 2 mm we are applying for all the dimensions. You can see a 2 decimal, and here we are giving a 0.2. So this is the dimension, how it looks like. But primarily our intention is not this. Our intention is try to interpret it. So if we are going to see this particular drawing, only we have a one tool, that is tolerance. The 50 plus minus 1 or 20, 80, whatever. But one tool is enough, and how can we prove that is not enough? What about this 20 diameter? Look at the 6 different holes and what is the coordinate system? So for this bore, can I assume that this is my coordinate system? Can I assume that the coordinate system is here? Can it be here? Can it be here or where? Nobody knows, but the reality is that is not being addressed by this particular method. What about the position of this hole from this edge? The 20 typical dimension here is measured how the flatness is getting varied, how the straightness is getting gauged. What about this hole's position from this edge, which is 20? What about both the positions simultaneously from the edge? What about from the top, its typical dimension? Nobody knows, because all the tolerance is being controlled across a rectangular tolerance zone. The 0.2 which you are seeing from the center, from both the direction, because if you see here also 0.2 can deviate, here also 0.2 can deviate, but from the center it is 20 and 0.2. But what about the across the different other direction? You are getting maximum in the diagonal direction, which is not 0.2. That is the problem. So why should the permissible radial offset of the axis of a bore be greater than the other direction, but in a one direction? So it shouldn't be. The classical tool provides no meaning of linking the location. That is the features. There is no interdependencies, and that is the problem which we need to fix and address. That is critical. But if you talk about a critical complex part, there this particular scenario will be pretty challenging. So you cannot even imagine complex part with general tolerancing. So but a clearance bore gets larger and it can be further offset. So there is no medium to restrict this and fix it. The classical tool provides no means for managing feature forms. The classical tool provides no meaning for researching and refining feature functionality. Because of that, you cannot guarantee the fitment and function. And assemblability also is a question, and you will be in dilemma. So another question is, what about this particular holes? The bore 1 really bore 1? So how can you say that the bore 1 is typically bore 1? Because there is no fixed location with respect to which you do manufacture and you do the gauging and you do referenced. So what about the bore 3? That bore 3 is a bore 3 and so on. So is this a bottom of the part, or is this the bottom of the part? So is this the bottom of the part, or this is the bottom of the part? Nobody knows. We have controlled a symmetrical part in an asymmetric way. This is an absolute symmetric part, but you know the complete controls which we have done is in an asymmetric way, and the complete frustration and confusion for the manufacturing and the inspection people starts. So as a result, classical tolerancing leaves us the beholden to the tribal understanding, means a wrong understanding and interpretation method. But the GD&T, if you compare the frustration and the power of GD&T, just does the magical touch. And GD&T frustration is, the GD&T is complex. This is a myth, this is not truth. Just I will guarantee that mathematically I can explain you GD&T. So GD&T's frustration and myth, you can see most of the people, they think that GD&T is complex. GD&T is basically boring. GD&T is often used to decorate or paint your drawing rather than encode the function. They are absolutely right because they think like that. And GD&T is generally interpreted rather than decoded. They are also right because they think. And GD&T opportunities is like this. The GD&T encourages fault-tolerant design and can guarantee assemblability and function. And GD&T reduces manufacturing cost through unambiguous communication and looser tolerance. So GD&T gives you a higher tolerance so that you can play around. GD&T never only gives a loose tolerance. And GD&T turns the 3D metrology inspection system absolutely reliable in the scientific process.